Hi, I'm Jeff Gilbert, President of Azimuth Solar Training. Welcome to the Fundamentals of Solar Hot Water. This one-hour video was produced for Virginia Tech and Virginia Cooperative Extension as part of their regional efforts to assess opportunities to integrate renewable energy generation for farmers and rural small businesses. The scope of this seminar will include what solar hot water is and how it works, the history of solar hot water, industry growth trends, the solar resource in the United States, the different configuration of solar hot water systems, solar collector technologies, balance of system component packages, incentives for solar hot water systems, the economics of a sample solar hot water system, and 3 different case study examples of solar hot water systems. So what is solar water heating? Well, it's using the sun's radiant energy to produce hot water as a supplement to conventional water heating. The key word here is supplement. Since the sun doesn't shine all the time, given cloudy days, we always have to have a backup heating source. This screen shows the parts of a solar water heating system, and a little animation will show its function. The sun shines on the collectors, and they get hot and transfer their heat down to a solar storage tank. That hot water is then boosted, if necessary, by a backup water heater, and then the hot water goes to the load, in this case a little boy taking a bath. So why use the sun to heat water? Well, as it turns out, it's the lowest cost alternative in most cases. Also, there are no emissions from the heating of water from the sun. The collectors last about 20 years or more, and these systems can enhance the value of your property. Finally, grants, tax credits, and other incentives nationwide can help reduce the upfront cost, increasing the return on investment for solar hot water. A little history of the solar hot water industry. It actually started all the way back in 1767 when Horace Benedict de Saussure built the first solar collector. This wasn't an actual working solar water heating system. It was just an insulated box with a glass window on top, and he wanted to see how hot he could get the air inside. I don't know the actual temperature, but he was able to achieve much hotter temperatures, probably in the order of about 300 degrees Fahrenheit. And this proved that the idea of this greenhouse box would work. And then in 1892, the Climax water heater was the first commercial system sold in California for $25. These were the first solar water heating systems. And this design is still being used today by one manufacturer. Between 1920 and 1940, mostly in Southern California and also in southern Florida, the solar water heating industry actually grew very quickly, and many systems were installed on roofs. This changed, though, after the 1930s for the most part, when the United States became electrified. Once we had electricity throughout each of the states, there wasn't really a reason to have solar water heating on the house when you could just get a very inexpensive fuel, electricity, to heat water on demand, and no worries about cloudy days. Now in the 70s, we had our oil embargo, which was our energy crisis, and President Carter enacted a 40% federal tax credit. And this actually made the solar water heating industry boom rapidly. In fact, companies were coming out of the woodwork, some less than reputable. But all this changed when President Reagan came into the White House. He had a different idea of the way to lead the country. And in 1986, he removed the federal tax credits, and the industry all but died. Most companies went out of business. Only a few stayed in business, and for the most part, they were just continuing to maintain the systems that had been installed before. In the year 2000 and beyond, we saw a resurgence of the growth of the industry, and it's been going strong ever since. This is primarily due to the increasing cost in fuels for heating water.
This graph shows the growing trend for the growth in the industry in more detail. And so here we have annual solar, water, and space heating installations in the United States between the years of 2000 and 2010. And you can definitely see this upward trend. From the year 2000 to about 2004, there were some ups and downs, but since that time, it has been an uphill climb ever since.
If we look back even further, back to 1974, we can see where the Carter 40% tax credit was in business, and then suddenly it died, and literally there was just sudden death, shown here at 1985, and the industry just sort of puttered along until about the year 2000, and you can see that steady growth that was represented from that earlier graphic. Interesting to note, California, Hawaii, Arizona, Puerto Rico, and Florida combined represent 50% of the national demand for solar water heating systems, and all the rest of the states make up the other 50%. Here we're looking at a map of the United States as its solar resource. Down below you can see the scale, and that's kilowatt hours per square meter per year of sun irradiance. And you can see in the lower left, that's the desert Southwest, you can see the much redder and oranger colors. That would make sense. And up in areas like Seattle, they get very little sunshine. That has a bluish color. I've also shown, or NREL, put also Germany on this map. Now, why do we have Germany there? You can clearly see that it has a terrible solar resource, but it's been included on this map because Germany is, at least has been, the largest solar market worldwide. They have more solar installed per capita than anywhere else. Why? They have a terrible resource, and yet they have such a great solar industry. Primarily, it's because their government strongly supports solar. So with strong incentives comes a strong industry. This graphic shows the fuel resources that we have for heating water. This large cube represents the amount of sunshine that we get, solar energy, on an annual basis. And these boxes over towards the left represent coal, oil, natural gas, and uranium, respectively. Those are fixed amounts of fuel that we are extracting from the ground and using. They're being depleted. But this giant orange cube representing solar energy comes to us renewed every year. Now, the small blue cube down at the bottom there represents the amount of energy that we human beings use on an annual basis. Now, relatively speaking, it looks like it's a very small amount, but that's not true. We human beings actually use an amazing amount of energy annually. It's in the order of 400 quadrillion BTUs. So if you wrote a 4 and then 17 zeros after it, that would represent the number of BTUs that we use roughly on an annual basis. It's an amazing amount of energy. The solar window is a way to describe where the sun's going to be at any time during the year. Now, in the summertime, the sun has a much larger arc through the sky. You can see here represented by the June 21st sun path. And then in the wintertime, the shortest day of the year is December 21st. It has a much shorter arc through the sky. But all the points in between, all the possible locations of the sun, are what we're interested in when we're siting an array, a solar collector array. We want it to face towards the sun. And in the United States, that means that we want the array to face generally to the south, because that's where the sun hangs out. It rises east-ish and rises through the sky and sets west-ish, but it's always going to be in the southern part of the sky. We can also describe the solar window a bit more refined by looking at just 6 hours in the middle of the day. If we look at the hours between 9 in the morning and 3 in the afternoon, these are the hours that we're most interested in. It's very important that we don't have any shadowing or very minimal shadowing on our array during these hours, because this is where most of the sun's energy comes down. 3 hours before noon and 3 hours after noon. There are 5 different solar hot water system configurations. The first is called an integrated collector storage, or ICS. These are also referred to as batch water heaters. The second is thermosiphon systems. The third type is open loop systems or direct solar hot water systems. Then we have closed loop drainback systems and closed loop glycol systems, which are also referred to as indirect solar hot water systems. I've colored these 5 systems as either being blue or red. The blue represents open loop systems, which are systems that use potable water as the working fluid and always have a fresh supply of dissolved oxygen. So it's important to use stainless pumps or bronze pumps. And the red ones here represent closed loop systems, which use the same fluid circulating in a closed loop. So in this case, the dissolved oxygen is pretty quickly depleted, and cast iron pumps can be used for this, saving a bit of money on the installation cost. Integrated collector storage systems, or ICS, and these are also called batch collector systems, are solar collectors where the hot water storage is actually up in the collector. These are very simple systems. You can see here from the schematic that the cold water is fed into the bottom of the collector, and then out of the top, where it's hotter water, that's what goes as a preheat to a backup water heater. So this is the simplest configuration, fewest parts. These are most appropriate down in tropical climates, or like Florida, Southern California, in areas where you don't get any significant frost or freezing, because these are not protected. This is potable water that's flowing through the system. And these are very economical systems as well. Thermosiphon systems are less common in the United States, in fact pretty rare. They're pretty common in developing countries though. The idea with a thermosiphon system is to have the storage tank physically higher than the collectors. And in the middle of the day when the sun is shining, the water in the collector gets hot. And again, this is usually potable water. The water gets hot and it rises. As water gets hotter, it becomes more buoyant and rises, and it goes up into the storage tank. And then the cold water or cooler water that's in the storage tank from the bottom of the tank would be fed down to the bottom of the collectors, and you end up with a naturally flowing convection loop that's driven by the heat of the sun. These are simple systems, and similar to batch heaters, these are most appropriate in warmer climates. They're really not protected from freezing conditions for the most part. To the lower left, there's a picture of a system that is more tolerant of freezing. Those tanks, that horizontal tank is very well insulated, so there's a bit more protection from freezing. But it's still best to keep these in warmer climates so that they do not have a freeze break. The economics of these systems is pretty good. It's in the middle of the range, the lower to middle part of the range. We'll talk about cost at the very end here. And also, it's important with these types of systems, as with batch heaters, that the water quality be good, because it's fresh water flowing through the system and the system gets hot. You can get scale deposits and lime deposits, which can clog up the riser tubes. Open loop systems, actually all that we've talked about so far are open loop systems, but when we refer to a system as just being open loop, usually what we're referring to is a system where you have a collector or collectors, usually up on the roof. These are very common down in Florida, and they're very simply piped to the water heater, which would be in the house usually. And the way they're piped, as you can see on the schematic, is that the cold water is drawn from the bottom of the storage tank where it's relatively cooler, and that's the water that's pulled up to the solar collector, and it gets heated and brought right back again. There's a controller and a pump that turns on when there's enough sunshine. It uses temperature sensors to turn on and circulate the water when the sun is shining. Again, this is open loop, so you want to make sure that when these systems are installed that the water quality is good. If the water is hard, having a lot of dissolved minerals, those minerals can deposit and clog up the collector. If you were down in Florida and you had a problem with hard water, then you might want to install a closed loop system, which I'm going to talk about in just a minute. The economics of these types of systems is good. As you can see, there are very few parts to the system. There's just the collectors, the piping that connects, and a small controller and pump. Drainback systems are a closed-loop system that are a bit more complex, and these are well suited for freezing climates. So let's say Vermont, where it gets really cold in the wintertime, this would be a perfect type of a system. The collectors actually empty themselves every time the circulator pump turns off, and this is its freeze protection mechanism. At night, when it gets cold and the pump is off, the collectors are empty. The water will actually settle down to the level of the reservoir. There's a reservoir, small reservoir tank, usually around 10 gallons or so, and that is about half full with water. During the day, when the pump turns on, it will draw that reservoir of water and circulate it up through the collectors, and heating that and then bringing it down. There's a heat exchanger, usually in the solar storage tank, but it could also be built into the drainback reservoir. There are a couple different designs. A couple things to note about drainback systems. The piping has to continually flow downhill from the collector, and this is so it can properly drain. If there are any bellies, as we call them, in the piping, water would not flow all the way down and would remain in the pipes, and during a freeze condition it would cause the pipes to burst. So in this case we always have to have pipes flowing downhill. Another interesting quirk, I guess, about drainback systems is that because there's air in the system, it's not completely filled up. There's this half-full reservoir. There are bubbles. When the pump turns on, it pushes air out of the collector and makes a gurgling sound. It's not usually too bad, not too loud, depending on how it's installed or where it's installed, but it is a notable sound. You can hear it. And some people don't like that, to be able to hear anything. Closed-loop glycol, or indirect systems, are the most common in the United States and Europe. In Europe, they account for about 90% of the total market, and here in the U.S., maybe 80%. We have open-loop systems and also drainback systems down in the southern states that make up a fair amount. In a glycol-based system, propylene glycol and water as a mixture is the working fluid of the system. It circulates through the collectors and then down to a heat exchanger that is usually located in the tank, or it could also be located external to the tank, and then there'd be a second pump, a potable water pump. I'll show a schematic of this in a later slide. These types of systems differ from drainback systems in one way, in that they are silent in their operation. Usually the pump is the only thing that makes some noise, and in some cases you literally have to have your ear up against it to be able to hear it. The freeze protection is just about foolproof here because we have this propylene glycol and water mixture that is, depending on the concentration, can get freeze protection down to minus 30 degrees Fahrenheit. So it's and even then it's a slush sort of freezing, not a hard freeze like water does all by itself. So this type of system is applicable anywhere in the world, really. Let's look a little bit deeper into glycol-based systems, since they are the most common type of system. I've shown here all the working parts of a glycol-based system. Here we can see the collectors up on the roof. Most commonly, they're installed on the roof of a house or a building. And we have the solar storage tank, in this case shown in the garage. Also shown here is a heat exchange appliance. This is an example of a system where the heat exchanger is external to the tank. And then we have the backup water heater. You always need some kind of a backup. And then we have the connecting piping that brings the heat to and from the collectors to the tank. Now what I want to do is break out the components even further so we can look at the inner workings. What we're looking at here is a Two-tank arrangement. We have the solar storage tank with the heat exchange appliance mounted to it, and then a smaller backup water heater. In this case, we're looking at a product by a company called Heliodyne. They specialize in external heat exchange appliances, as they call them. If we pull away this heat exchange appliance so that we can look at it in a little bit more detail, and then also connect the piping that's typical to a solar water heating system, we can see it, how the piping would go up to the solar collectors that would most probably be mounted on the roof. And then we see the piping that goes from the heat exchange appliance to the solar storage tank. And then we have the normal plumbing that would be in place for bringing fresh water to the tank and then off to showers and laundry and other faucets. If we pull away the front face of this particular heat exchange appliance, we can see the inner workings. We have a glycol pump. This is the antifreeze pump that circulates the fluid to and from the collectors. Then we have a water pump. This is circulating water from the solar storage tank through the heat exchanger in this system. The heat exchanger is this U-shaped tubing. And then we have a pump controller. The controller is the brains of the system that turns on and off the circulator pumps based on readings that it gets from temperature sensors. There'll be one temperature sensor up at the collectors and one temperature sensor reading the water temperature at the bottom of the solar storage tank. And whenever there's favorable conditions, it turns on the circulator pumps. All right, so now we've made everything disappear except for the piping. And you can see the way it's drawn here, the glycol loop is separate from the potable water loop. The fluids do not mix with each other. The tubes are actually concentric in the heat exchanger, and they transfer heat very effectively. This is what's known as a tube-in-tube heat exchanger. Systems can also be powered by a photovoltaic module, as you can see here. And this PV module would be up right next to the collectors, seeing the same sunshine that they see. And then a number of the components, like temperature gauges and pressure gauge and flow indicator, circulator pump, check valves, all these components would be put into this package that you see there to the right, upper right. In the old days, we had to assemble these completely piece by piece by piece. But now there are products that we can just buy off the shelf, and it's more of a plug-and-play arrangement. There's one variation of a glycol-based system that I think is worth mentioning, and it's called a geyser pump solar hot water system. It's still, your basic configuration of solar panels, usually on the roof, and a tank, usually somewhere down below, oftentimes in a basement. But what makes this type of system work is percolation. It's like the old coffee pots where they would percolate. In this type of a system, the fluid isn't pressurized. It's actually at a vacuum, which causes the fluid to, in a sense, boil at much lower temperatures, like 100 degrees Fahrenheit, which is barely warm to the touch. That's when the temperature of this fluid boils, and the boiling creates fluid bubbles which rise, and they go up in this little geyser pump stack, and that percolation causes the fluid to flow and circulate. So in this case, there's nothing to plug in, there are no controls to operate. It simply works by the sunshine. The solar fraction describes how much energy is coming from the sun as compared to energy for hot water coming from conventional means, like your backup water heater. And typically, with solar water heating systems, we're looking for solar fractions between 55 and 75%, depending on how big the system is and the hot water load of the family or building being served. So you can see in the bar graph, in the winter months, let's look all the way to the left with January. We're getting, it looks like about 38% or 0.38 of the total solar fraction. This is because in the wintertime, usually the hot water loads are a bit higher. In other words, people taking longer, hotter showers at the same time that we have less sunshine. So the solar fraction is going to be less in the wintertime. And in the summertime, if the system was sized properly, we're going to be getting 100% or close to 100% through the summer months coming from solar. The text down below takes the analysis a little bit further. If the average house uses 15 to 25% of its energy for heating water, then what we're looking at here is how much total contribution solar water heating will be as compared to the total house energy use. So if we had a solar fraction of 65%, and let's say that heating water was 20% of a house's total energy bill, then 65% times 20% would mean that solar contribution for heating water is 13% of the total household energy bill. All right, the different types of solar thermal collectors that are out there in the market. For the most part, what we deal with are these two, either flat plate collectors or evacuated tube collectors. Now we'll talk about evacuated tubes in a minute. The other two types of collectors, unglazed tube mat collectors and integrated collector storage collectors, are less common. They're really just applicable for southern Florida, southern California. The unglazed tube mat collectors are most commonly used for solar pool heating. As you can see, there's no frame and insulation and a glass window on top. These are just plastic tube mats that are exposed to the sun, and usually pool water flows through them and just heats up because they're black and sitting in the sunshine. There's one company that uses the same collector material for making domestic hot water heating collectors, but again, they're just applicable for sunnier states, usually the Sunbelt states. So between the flat plate collectors and the evacuated tube collectors over on the left, we have market share of about 85% going to flat plates and about 15% going to tube collectors. This is changing. It's changed over the last 5 or 6 years, giving a bit more market share to the tube collectors. They've become more common as the prices come down. Usually Chinese products at very low cost are coming into the United States, and they have a different appearance. They look a bit more futuristic. Some people kind of like the appearance of them. I'll talk a bit about the differences in efficiency on a slide coming up. Flat plate collectors, as I said before, are the most common type of solar water heating collector in the market in the United States. These are made out of usually extruded aluminum frames that are insulated and have a tempered glass window on top. These are very rugged. Once they're installed, they're very rugged, very unlikely to break due to things like hail or the weight of snow or anything like that. If a large branch were to fall off a tree and land on them, then it would break them. But tempered glass is very strong when it's held in place by an aluminum frame. These are tested to withstand golf ball size hailstones going at 50 miles an hour, so they're very robust. The working part inside of a flat plate collector is called the absorber and is made of copper tubing with either copper fins or sometimes now aluminum fins. There's a way of using laser welding to connect aluminum to copper in a way that doesn't cause galvanic corrosion. And the surface, the part of this collector or absorber that sees the sun, has either black paint to just get hot from the sun or some special coating. The life expectancy of solar water heating collectors is about 25 years, depending on how they're cared for. There's not that much maintenance, but there's a little bit. We'll talk about that later. The weight of a solar collector is somewhere between 120 and 160 pounds, totally full, with fluid in it. One manufacturer is now making polymer collectors so that they're a bit lighter. But generally speaking, if you're wondering how much dead load these are going to provide to a roof, think in terms of 120 to 160 pounds. For operations and maintenance for collectors, for the most part, just change out the glycol every 5 years or so. This is just to make sure that it doesn't become acidic due to extreme temperature conditions during stagnation. For open loop systems or drain back systems, there really isn't any maintenance. Here's a quick animation that just shows the fluid flow through a flat plate collector. This is a harp design, or a header riser design. The fluid comes in from one corner, equally rises through all the riser tubes, and then heads out the other header corner. We always want to come in on one corner and out the opposite corner, and that's so that we have equal flow and equal pressure through the whole collector. There are other collector designs that use a serpentine pattern, basically just a zigzagging back and forth tubing inside. But this is the harp design is the most common tubing configuration for flat plate collectors here in the United States. Evacuated heat pipes differ from flat plate collectors in that they are made up of a number of tubes. These are glass tubes that are like long, 6-foot long thermos bottles. They are evacuated. All the air has been sucked out of them. In some cases, this particular design from Apricus uses a double glass wall, and the airspace between these glass walls is evacuated. In other evacuated heat pipe technologies, different manufacturers might actually evacuate the whole space inside, where the fin tube is as well. With evacuated heat pipes, the idea is to transfer heat from the tube up to a bulb that's at the top, and that bulb is usually clamped within copper tubing, and the working fluid will pass through that copper tubing, extracting the heat from the bulb. I won't go too deep into the workings of evacuated heat pipe systems, but just to say that they have some advantages. They are very efficient in extreme cold temperatures. They have an advantage that it doesn't matter how cold it is outside or how windy it is. Inside of that thermos bottle, inside of that tube, it's very hot as long as the sun is shining. One of the disadvantages with evacuated heat pipe technologies is that they can't afford to stagnate, meaning that the circulator pump for the system can't be off for a long period of time in full sun conditions. Obviously, it's going to turn off every night. But when the sun is shining and these tubes are exposed to the irradiance of the sun, they need to have the heat drawn off and away from them, otherwise they will overheat and they could actually damage themselves. One of the ways to avoid damage from stagnation is to use a heat dissipator, as Apricus does. You can see that this is just a fin tube configuration that dumps heat to the air. It basically finds a path for the heat that gets collected. Comparing flat plate collectors to evacuated tube collectors is rather subjective. There are scientific studies that have been done to try and figure out which is better, but the truth is they both have pros and cons. They both have advantages and disadvantages. One particular study that was done has results shown here on this chart. In the y-axis, we have efficiency from 0 to 100%, and in the x-axis, we're looking at a comparison between the incoming temperature of the fluid and the temperature of the ambient air. So the difference between those two is described on the x-axis scale and goes from 0 to 150. In the middle, in this blue shaded area, is the temperature range that most solar domestic hot water systems operate. They may be trying to get the potable water up to 130 or 140 degrees Fahrenheit, and the outside temperature might be somewhere between 60 and 90 degrees Fahrenheit. The technology that performs the best in this particular test is shown by this black line, the one on top, and that is a flat plate collector with a selective surface, that material that absorbs very well but emits very little. The red line, almost parallel to it, below it, is also flat plate technology with just a black painted absorber. The purple line, you can see, has a shallower slope, and this is for an evacuated heat pipe. The efficiency in warmer conditions, under sort of the easier conditions of heating water, is actually less than a flat plate collector. But where the evacuated tube really shines is under the most extreme conditions, when it's really cold and windy outside and you're trying to heat the water to a high temperature. In that case, then the efficiency of an evacuated tube is going to surpass that of a flat plate collector, and it has its advantages. Also not shown here is the comparison of price. In most cases, the evacuated tube collectors are more expensive than the flat plate collectors, at least for the high performance ones. Oh, the last line shown on here is the green line. This is for an unglazed pool collector. Remember, these are the plastic tube mats that are most commonly used for heating swimming pools just during the summer. These types of systems can be the most efficient during the middle of the summer when the air temperature is hot and they're trying to just raise 75-degree pool water up to 80 degrees. In this narrow range of operation, they're very efficient, but they don't work really at all under cooler conditions. You wouldn't want to try and get domestic hot water up to 130 or 140 degrees in the wintertime in Vermont with an unglazed pool collector. It just can't do it. Anytime a breeze comes along, it would take away the heat that had been collected. Hot water pump stations. What these are, different products by different manufacturers. They all do basically the same thing, and that is to take a bunch of the components that are common to usually glycol-based systems. You have a couple temperature gauges, a pressure gauge, some valves, oftentimes one or two pumps, and a differential controller, the brains of the system. All of these parts are often packaged into something that you can mount or hang on the tank or on the wall, and makes the installation go much faster and look more professional. These are available in residential as well as commercial-sized pump stations. Data monitoring, well, in the old days, all we had was temperature gauges and pressure gauges and possibly a flow gauge. And everything was, you had to go up and look at it, right at the system, to see how it was performing. Then we had controllers that had digital displays on them that would give us temperature readouts and sometimes other information, and that was a little bit better in the evolution of data monitoring. And then finally, we have remote monitoring systems, and now actually web-based systems where a number of sensors will send signals over to a data monitoring box, and those signals are then sent out through a router to the internet, and you can go to a website and graphically see the performance of a solar water heating system at any time from anywhere. And this is really kind of the future of monitoring. This is also usually necessary if someone wants to sell SRECs. I won't be able to get into that really, but an SREC is a solar renewable energy credit, and these are available in some states that have renewable portfolio standards. The idea here is that the greenness, the environmentalness of the energy from a solar hot water collector is a tradable commodity, and you can actually get money from a broker, someone who needs or wants to buy these credits. Can buy them from you, and you can actually get cash money for the greenness of the performance of the solar water heating system. There are a number of different mounting configurations that you can use. The first one here is what we call a flush mount array, and this is where the collector is at the same slope and orientation as the roof. It's the most common way. It's the simplest installation. We could also tilt up the collectors if the roof doesn't provide us a good orientation and tilt that we want, or if we need to do a ground mount, not shown here, but we can really pick the orientation and tilt that we need with some tilt-up racking. This is an example of a ground-mounted system. This is actually for heating an indoor swimming pool, and the collectors would not normally be at such a shallow tilt angle, but this house is located right on a golf course, and the homeowners association required that the array be at a very low angle so that it wasn't too visible. And you can also see in this picture that it's shaded. This is late in the day. Normally in the middle of the day it's getting full sunshine. And then we have smaller commercial systems. One of these pictures, the one in the lower left, is Fenway Park, home of the Boston Red Sox. And that was a sort of a mid-size commercial system for the hot water that they use there at the stadium. And then we have much larger commercial and industrial solar hot water systems. The one on the left is flat plate collectors. The one on the right represents the evacuated tube collectors. The incentives for solar water heating systems. If you go to www.dsireusa.org, you'll come to a database that shows all the incentives nationwide, statewide, even countywide, including tax credits, rebates, grants, low-interest loans, anything that would be an incentive for solar and other energy efficiency technologies is summed up on this website. It's a wonderful website. What I'd like to do now is walk you step by step through the economics of a sample solar water heating system. And this system will be in Virginia, rural Virginia, and I'm going to be using Richmond as the data set for the meteorological information that I'll be using for this analysis. And I'll show you in a minute where I get that. So this system will be a residential 4-person system that offsets propane as the fuel. There are a lot of homes, farms, and businesses in rural Virginia that use propane as the fuel. So that's why I chose propane. Okay, so let's start out with the initial capital investment. First of all, we have a sample system where the installed cost is $9,000. And what you get for your money here is 2 4-foot by 8-foot solar collectors with an 80-gallon storage tank, and then, of course, all the other balance of system components that go with that. It's $9,000 installed. It's possible that you could pay more or even less for a system, but I think this represents a typical installed cost. Next, we have the value of the federal tax credit that is available for the next couple years in all of the United States, because this is federal, and that is a 30% tax credit off the gross cost of the system. And that has a value of $2,700. So when we do the math, the net cost ends up being $6,300. That's our out-of-pocket initial capital investment. All right, so that's the beginning. Now let's look at how the economics come out over the 25-year life of the system. So we have annual savings because now we're offsetting the use of propane. The value of the offset propane is going to be calculated at a rate of $3.75 per gallon. And I just went online to find out the latest rates. It actually went up above $4 per gallon of propane, but I decided to use $3.75 for this example. And I'm going to be offsetting 153.1 gallons of propane. And that part of the analysis I'll show you in just a minute where I got that number from. And so when you multiply those together, we get $575 per year value for this system. Now let me show you where I got that information from, the 153.1 gallons. I used a clean energy project analysis software called RetScreen. That's from RetScreen International. This is a software package that was put together by the Canadian government to help people do economic and performance analysis for renewable energy and energy efficiency technologies. And this is a free downloadable software. You can just go right online and download it and begin using it. It is a little bit tricky, but it's certainly a useful software, and it's free. It's based on Excel, so it should be familiar to follow, just filling in the blanks. And the calculations are done behind the scenes. This is the front page where you enter the system information. And I chose Richmond for the location. And down at the bottom, you can see all of the meteorological information about Richmond. So for the whole year, each month, we have air temperature, relative humidity, daily solar radiation, atmospheric pressure, wind speed, earth temperature, heating and cooling days. All that information is in its database, and this is taken from airports or some location in or near Richmond over the last 10 or 20 or 30 years, and it's been put together in averages. So that's the information that I'll be using. Now, in this analysis, there are several tabs down at the bottom, and the main one where all the numbers get entered is in the energy model. And so you can see here, I won't go through all of the data that I put in, but you can clearly see this is for a house, occupancy of 4 people, 100% occupancy, meaning they live there all the time. And so I chose the size of the system parameters there. And I chose the collectors, and there's automatic data that gets populated when you choose the collectors. And the main thing I want to point out is down here at the bottom. This system will produce 10.2 million BTUs per year, and there is a 78% solar fraction, which is pretty darn good. Now down at the bottom, you can see that I chose propane as the fuel. And there's a base case and there's a proposed case. The base case is, let's say that this was a home where propane was already being used to heat the water, and now we're going to retrofit a solar hot water system to that. So that's the proposed case. And in both cases, we're going to use propane as the backup fuel, and we have a 70% efficiency for the hot water heater, which is pretty typical. But you can see in the base case, to heat hot water for a family of 4, you would need to burn 197.2 gallons of propane. And by adding solar to it, now we only have to burn 44.1 gallons per year. So you can see the nice reduction there. And then down below, you can see where I added the cost per gallon as $3.75. And then below that, it does a quick calculation to say that the money that you would spend in buying 197.2 gallons of propane would be $739. And of course, the reduced number is $166. So in my analysis, what I did is I subtracted 44.1 gallons from the 197.2 gallons, and that's how I ended up with that 153 or so gallons that I used in my analysis. So where we left off was a value of offset propane of being $575 per year. And we saw where that 153.1 gallons of propane offset came from. Next thing I want to talk about is the cost of annual system maintenance. I put in $75 per year, and I think that's fair. I've lived with solar water heating for over 10 years, and I've worked on systems for the last 20 years. And what I've learned is that if a solar water heating system is installed and designed properly, it should be relatively maintenance-free. You may have a sensor go bad after a couple years. Certainly after about 5 years on glycol-based systems, the antifreeze should be replaced. And maybe after 10 years, a pump will go bad or the controller or something like that. But these systems, again, if they're designed and installed correctly, they should last and be maintenance-free for their full 25-year life, except for just regular wearing out of parts. So $75 per year for maintenance. We do the math. We come out with a savings of $500 per year. And a simple payback would be our initial capital investment, $6,300, divided by that $500 per year. We come out to 12.6 years. And that may seem like a lot. Most people would say, well, gosh, I don't want to invest in something that doesn't have, a 3-year payback or a 5-year payback. And certainly in other states, solar water heating systems do have paybacks that are that quick. Washington, D.C. and Maryland have paybacks that are very quick. But Virginia does not have any incentives specifically for solar water heating, so it's a bit tougher. But that doesn't mean that solar water heating isn't still a good investment. So let's look at the complete analysis. So this is 12.6 years to get to the 0 point for your out-of-pocket. Now what happens with the other 12.4 years that are left? If you multiply those times $500 per year, now we end up with a net positive return of $6,200. So you not only got all your money back, but you made some money. And the neat thing about this is, contrary to taking money and putting it into the stock market or a mutual fund, with this, you do not pay capital gains tax. There is no capital gains tax on this because you're not actually getting a check. What you're doing is actually reducing the amount that you were going to pay anyways. And so basically you're saving that 15% that you would have had to pay if this money was put into some kind of a stock or mutual fund. This first case study that we're going to look at is a very typical residential solar water heating system. In this case, it was for a family of 4 in Lovettsville, Virginia, and it was installed back in 2003. You can see from the picture on the left that the solar array was made up of 3 collectors and fit very nicely on this mudroom addition that was installed on the house. The system components are listed here. You can see that there are 3 collectors, a 120-gallon storage tank, which I'll talk about in a slide coming up, a circulator pump, 4 gallons of antifreeze, and a bunch of other valves and components. The final price of the system was $78.50, which is significantly less than the price that I talked about in a previous slide. And this is because 8 years ago, the price of solar water heating systems was much less because the price of copper, aluminum, and steel were much less. Here we have a piping schematic that shows all of the components. It's only showing 2 collectors in this drawing, but of course there were 3 on the roof. One important thing to note in residential water heating systems is that it is important to have a bypass valve, shown here just above the backup water heater. And this is so that if service needs to be done on the solar tank, you can simply bypass it and separate it from the system and still have water going to the backup water heater. Another very important component of this system and any residential system is to have a tempering valve, and that's also installed just above the backup water heater. This is a thermostatically controlled valve that adds cold water to the hot tank water in the case that it exceeds 120 degrees or whatever the temperature that it is set for. This is to avoid the chance of scalding. These 3 photos are just close-ups of the thermal storage tank and the piping associated with it. The piping may look rather complicated, but it is rather simple. There's simply a cold water feed going to the bottom of that brown storage tank, and then the hot coming out of the top of the storage tank on its way over as a preheat to the backup water heater, which is insulated in this picture. We use 2 immersion type heat exchangers on this tank, and they are removable for servicing. The solar storage tank was a 120-gallon Vaughan stone line tank, and it literally has a stone lining. It's actually a cement lining about a half-inch thick, and this acts to greatly reduce corrosion of the tank. It protects it for about 20 years typically. In the bottom you can see that we have this double wall immersion type heat exchanger, and the tank has 2 inches of polyurethane insulation, giving it an R16 value. The collectors have the specifications shown below. The fluid capacity for these smaller collectors is just under 1 gallon apiece, and the dry weight is 108 gallons. These are the smallest collectors that Heliodyne used to make. They no longer make this size. It's about 3.5 by 7.5 in size. The second case study that we're going to look at is for a small commercial building. This is an old farmhouse that was converted over to office space. It was actually the location of our office for a number of years. And you can see the collectors in 2 different arrays up on the roof. I took this picture the morning after a snowfall, about a 4-inch snowfall, and you can see that once the sun came out, the snow quickly shed off of the collectors. This is often a question that people have, how well do these systems work when it snows? They don't work at all when the snow is completely covering the collectors, but it doesn't take much for the sun to get the snow to slide right off. The 2 pictures that are to the left-hand side are of this old farmhouse before it was gut rehabbed, and then the 2 pictures to the right are the finished Enviro Center. This is a LEED Silver rated building that incorporates a lot of energy efficiency and passive solar design. The solar piping in the mechanical room looks quite complex, but it's actually simple in its design and all fit on a sheet of 4x8 plywood. This line drawing shows all of the components of the system. You can see the 2 arrays up at the top. Just below the 2 arrays is a thermal dump load. This is literally a baseboard radiator that was mounted right underneath the lower array outside, and the purpose was to dump excess heat in the summertime if it was not being utilized. And down on the lower left we can see the storage tank. This was a square tank, 500-gallon capacity, and had 2 immersed coils, 2 heat exchangers immersed and hanging in the tank. The tank was simply a thermal battery containing 500 gallons of water that did not circulate. And we have a boiler for backup for the heating zones, and you can see 3 of the radiant floor zones shown in the lower right corner. In the upper right corner we can see the domestic hot water tank. This is the backup for the solar water heating. This is another drawing showing the whole mechanical system for the building, including all of its controls, and the circled areas are the solar input. We did run into some problems during the installation of this system. We installed the solar heating system at the same time that the building was being constructed. During the construction of the building, before we had a chance to fill up the 400-gallon biodiesel tank shown here kind of on its side, we had a bad rainstorm, and it filled up this whole pit with water, and the tank floated and tilted on its side. We also had a problem with the clearance of the ceiling, making it very difficult for us to install the unions for the top of this tank. These are just typical installation problems that any construction site or solar energy installation might experience. In this third and final case study, we're going to look at a medium-sized commercial system that was installed at Fenway Park in Boston, home of the Boston Red Sox. You can see from this satellite view a look down onto the array, and then we've blown up the array so you can see it in a bit more detail. If you look closely, you might notice that it's actually 4 subarrays, 4 7-collector arrays that were actually independent of each other and pre-engineered, and then just installed together to look as a single system. A few statistics for this installation are that the roof faced almost due south, and it was installed in 2008 between May 7th and May 12th. The total collector area was 1,120 square feet, and the total thermal storage size was 1,600 gallons, 4 400-gallon tanks. It was estimated that the maximum daily production would be 1.1 million BTUs, and the load fraction would be 37%. The fuel that we were offsetting here was natural gas, and it was also estimated that 18 tons of carbon emissions would be avoided each year from this system. As with just about any commercial system, there are always challenges. In this case, where to put the tanks. The array had a nice location, but the tanks could not fit on the roof. The lowest picture there shows how busy the roof is. The upper picture there shows the tanks mounted horizontally into an attic space that was not being utilized. The installers had to cut a hole into the side of the attic to get access to it and install doors. The original hope for this installation was simply to drop a container right down onto the roof that would have all of the tanks and mechanicals pre-installed into it, and we would simply drop it in place and connect the piping to the array. But as you can see, the roof was very busy with existing mechanicals, so this was not possible. The pump stations and controls that we used for this are from Heliodyne and are very similar to the one that I showed before, except that this one is 4 times larger to accommodate a much larger array. The collectors were installed by crane up onto the roof, and these collectors were 4 by 10 in size, so this is the appropriate size for commercial systems. Here we're showing the tanks as they were installed in the attic space, and you can see the 4 controllers mounted on the wall in this lower picture. Again, each tank was 400 gallons. There were a total of 4 tanks, and they were mounted just underneath the solar array. In this last and final line drawing, we're looking at each of the 4 separate systems. We're only showing 2 of the 7 collectors in each of these line drawings, but you can see that they are really separate. We have the collector array, and then right underneath shows the pump station, and right under that is the tank for each of the systems. These 4 separate pre-engineered systems were all installed in parallel and as a preheat to the existing boiler. This concludes this video on the fundamentals of solar hot water. We hope you enjoyed this video and learned something about the technology. For more information about solar training programs from the Virginia Cooperative Extension, please contact John Ignash at the information provided here. I'm Jeff Gilbert, and thank you for joining us.